titanium-64. So we talk about, we stopped here. So this is the material model implementation. And so deflux, and we use the deflux subroutine and to mimic the EDM, the process, the heat transfer process. A VSD field is used to compute on phase evolution and phase fraction. So this is the subroutine VH hard. A V hard is used to compute the flow stress for different phases. And flow stress means the stress, the effective stress. Today we are going to talk about the experimental validation, and also this is the results. And then we move on to the next paper, and I'm going to show you how we use EDM to machine the non-conductive material. So usually EDM is used only for conductive material, but we have come up with the new idea, and to EDM, this is the non-conductive material. I'm going to show you. Right? So experimental validation. So here, last time I told you, whenever we do the numerical simulation of any physical processes, first, you finish your model, and your model needs to be, you need to do the convergence test to make sure your model, your simulation results are reliable. And reliable means that it will not change if you change the mesh. After you refine your model, after you do the convergence for your model, next step is that you need to validate the model. Right? So, and you need to, last time I told you to write down, to jot down what I just said. And first step is that do the convergence test to make sure your simulation results will not change if you change the mesh size. And second one, after the convergence test, and you need to validate your model. Validating model means that you need to use your simulation results to compare your simulation results against this is the experimental results. Because experimental results are the only reference that we can believe. Okay, so this is very, very important. Without the validation of your numerical models, you cannot get very, very high quality papers. Understand, everyone? Because you guys are very, very young and you do not know publishing a paper means what, right? If you are a professor, you know. If you don't publish paper, you will be killed out from the academia. The publication is very, very important. And since then we have this model, we have our simulation results, and then we want to do the experiments, and then compare the experimental results with our simulation results. Here is this micro EDM setup. So this one, Dr. Jagan, my collaborator, and this is the setup in his lab, and he used this one to do the experiments. Remember, when we compare numerical results and this is the experimental results, we need to make sure, and these two guys, they have the same machining conditions. This is very, very important to ensure this is a fair comparison. So this is here I'm going to show you. Okay, this is a CCD camera here, and so this is microscope, and so this is micron EDM here. So this is the pulse, the supply the pulse, and also this is a rotational motor. So this is the rotational motor here, rotation for the electrode. So the experiments here are the experimental conditions. The discharge energy, electrode type, and servo voltage, capacitance, electrode rotation. So these 5 guys can be controlled, and they are independent variables. You can control them, and then you can get this result. Okay, so this is electrode is rotating. The capacitance depends upon C. This is C value. And so we have, this is the servo voltage V. So discharge under the microjoule electrode type, the WC is a tungsten carbide. It's a tungsten carbide. So after machining, you use this condition. Okay, so this machining condition must be the same as we used for our model. After machining, and so machine surface, we will see a lot of craters on the surface. Our machine surface was analyzed, and we use ICEM to analyze the machine surface. The diameter of the micro craters of all experiments were measured using ICEM. And for each experiment, the average diameter of the 5 craters have been calculated. And why we need to measure so many craters? Because we want to minimize the randomness. Okay, this is some statistical issues here. We take the average of the diameter of 5 craters. So this figure shows the sample measurement of the crater size using ICEM image. And for the first experiment, in the previous table, and this table 3 shows the resulting data of measurement of crater size. So here is the crater size you can see, and for different energy levels, for different conditions, and we randomly select 5 craters. And so each of these craters, and we measure its diameter, and then we finally get an average value. And we need to use the average value. Okay, so here you can see, I don't know whether you can see it clearly or not. And you can see here is a crater, a crater. So this shows the level of discharge energy and the average crater size. So discharge energy and experimental the crater size. The discharge energy is corresponding. Here is the discharge energy, and this is the corresponding the experimental crater size. And table 5 for our simulation results. So this you must have the same result, same discharge energy. Okay, so this is discharge energy. Everything must be same. Discharge voltage, discharge current, and so this is TON time and TOF time. And so here is the predicted crater size. T1 is when this is the charge is what is voltage. So this is when it is on, the time when this is the discharge voltage is on. So this is the time when discharge is off. So based on the same material, same conditions for this table and this table. So this is from experiments. So this is from the simulations, and we select we do a comparison. Here is a comparison between experimental results and simulation results for different energy level. And we can see the simulation results are very close to the corresponding experimental results. So, and then that means this is our model has been validated. Only after we validate our model, and we can use this validated model to do the predictive modeling. Right? So here are the results and discussions. So here is the table 6, simulation results and predicted crater for higher energy level. As I told you last time, the predictive modeling usually is used to predict something that physically, experimentally not feasible, is infeasible. And so here is other discharge energy that is much higher than a higher one, and we can get this predicted crater size. Definitely, this model have been validated. So this is also a variation of crater size with this discharge energy. So here is predicted the crater size. Then next section is the phase transformation and residual stress. And this is the phase transformation here. You can see and STV11. STV11 is you can see you know, okay. So STV11 is STV11. So this is for the discharge energy level. STV1. STV1. Right? So STV1 here. STV1 is a fraction of marginality alpha prime. So this you can specify this as STV1. So STV11 is the discharge energy. The STV11. This is for discharge energy. So here is the von Mises stress distribution for the same energy level. STV11, this is STV11 is the phase, is a phase transformation. STV1 is a fraction of marginality alpha prime. So STV1, so for other conditions for other energy level. STV11, STV1, von Mises stress. And so here is a predicted heat affected zone for different charge level. Heat affected zone. So this is also here is residual stress. We want to calculate residual stress. So this is a crater. Okay, so this is the we use axis symmetric model. So here is axis, and here is this is a Gaussian distribution goes this way. So you can see this is a phase transformation, and from here to here, we want to see the residual stress distribution. And here we can see, for different energy level, and we can get from here to here. And we calculate, we see the residual stress distribution sigma x, xy. We see the sigma xx and the sigma yy. And then this is a phase transformation and residual stress for high energy level. For high energy level, as is the energy level is very, very high. So experimentally we cannot accomplish this. So we just use the model to predict. You can see this 72 microjoule is STV11. I'm sorry. So this is STV1. So this is von Mises stress distribution. So this is 72. Higher one, the higher energy level 12 45 microjoule. And for these three distributions, STV11, STV1, along with this is von Mises stress. So these are predicted the heat affected zone distribution. So this is sigma x from red point. So this is the stress distribution sigma xx, and sigma xy, and sigma yy. So these are pretty much what we have about numerical modeling of EEM machine of this titanium 6 aluminum and 4 vanadium. And based on this paper, what I'm going to test you is might be for this titanium 6-4, what are the physics we have? And after we machine it, what kind of physics we will have? And how to use Abaqus to build the model of EDR machine for this one. This is what I want you guys to answer. And use the axis symmetric model using 2D axis symmetric model for macromedia. Okay, everyone? Any questions so far? And also the methodology you should know. First, when you do the numerical simulation, you must do the convergence test. After the convergence test, you must use the convergent results. You must compare your convergent results with the experimental results and to validate your model. So this is then the third step is that use the validated model to do the predictive model. So this is the 3 steps, okay? And this one will appear in the final exam. Any questions so far?
No, I don't have any questions.
Question? Or no?
I said no, I don't have any.
Okay, good. And then we talk about the next paper. Next paper is also a very typical, the unique is that we use EDM to machine the non-conductive material. Non-conductive, this is the ceramic, aluminum nitride ceramic material. Usually, as I said, usually EDM is used for conductive material. But now we use EDM to machine the non-conductive. How can I do that? So I'm going to show you. So this paper, I want you guys to read this abstract introduction. What I want to tell you is that how we did this experiment. So experimental setup. So this is the experimental setup. How material specification, and so this is the aluminum nitride, and so this is the specifications for the nitride. And then how can we machine it? Right, so here I'm going to show it. You can see we have this is I'm going to test you this one method of preparing coating layer as assisted with electrode. So how to do that? We have suppose we have non-conductive workpiece, and then we add a thin layer of graphene and carbon paint, and bake in oven at this temperature for some time, and then we cool down to room temperature, and then we add a thin layer of carbon nanotube, and a layer of copper tape, then add a thin layer of carbon nitride, and a layer of carbon pulp, another layer of nanotube, so and a layer of the copper tape. So this is how we prepare. This is the material, the workpiece, and non-conductive workpiece. So this one I will ask you guys to do it, okay? To describe, and you should know how to get this result. So as I said, it's highly recommended that you do not copy the paste and crop from this material. I want you guys to use your hands to do something and to show me your understanding of this process. Okay? But if you want to do that, I want to do it otherwise, I'm okay. But I will not be happy. Just copy to some paint this tool and then crop it. You do not learn anything. Right? I want you to digest what I told you and to really use your hands to write down all these things to show me your understanding. So these will appear in the final exam. Why I want to test your understanding of this one, because it's unique. What is an innovative idea that we can use to EDM the non-conductive material? So this is the solution scale. Okay, once you can see, I will show you. So here is the hole, there are several holes here. So the entrance, so this through hole is a through hole. This is entrance that where we EDM it, and here is exit, and the pipe, the another side. This is exit. This is hole 2, hole 3, and hole 4, and hole 5. And so for different machining conditions. We also have done this one SEM image of set walls of drilled hole, the drilled hole EDM the hole. We will see, and you can see using ICEM to see the side of the wall of this hole. So here we also have done this is element analysis EDS. So use the EDS to check the element combination of this machine area. A lot of good work here. This combination. This is the combination carbon, oxygen, aluminum, copper, tungsten, and you can use the EDS, not EDM, EDS, and to get all these combination, the concentrations of these different elements. So this is pretty much about this paper. Okay, so this is very, very important. Questions? So as I said, that diagram will be tested. If there is no question, I'm going to talk about our third paper using EM to machine the bulk metallic glass. Bulk metallic glass is a very, very special material, very, very relatively new material. I'm going to show you. Here, usually to publish a high quality paper in a high quality journal, and now you need to have both experimental results and the numerical results. So this is a trend. This is what the NSF National Science Foundation wants us to do. Right? If you want to write a very, very competitive proposal, and the NSF officers they will ask you, hey. And I know a guy, and because suppose you are an experimental guy, and so the NSF officers will say, hey, I know a guy who is a modeling guy, and you guys can work together to have a better, more competitive proposal. This is always modeling and experimental come together. So, bulk metallic glass. For this paper, because the bulk metallic glass is very, very unique, I want you guys to know, okay? I will ask you, and what is bulk metallic glass? And why this guy is unique? And you should know why it is unique. So here, the bulk metallic glass is a solid metallic material with disordered atomic and glass-like structure. Amorphous is amorphous material. Amorphous structure. And is accomplished by rapid cooling the molten metal liquid. And during the rapid cooling, the metallic glass experiences a supercooled liquid state where the viscosity of the glass can be controlled over a wide range and creating the possibility for great flexibility in shaping process. So this is amorphous, okay? So this is what is metallic glass? How metallic glass is obtained. Additionally, the amorphous structure does not have the crystalline defects called dislocation, and which limits the mechanical property of most common alloys. Without dislocation, the BMDs are able to reach 3 to 4 times or more hardness and less stiffness than most common alloy. I want you guys to know, and so definitely I will test your understanding. I will ask you, what is metallic glass? How we obtain the metallic glass? And what beautiful properties metallic glass has? The beautiful property is high elasticity, high hardness, high fracture toughness, along with the superior corrosion resistance characteristics. This is the beautiful properties of BMD. Also, BMD is a strong heritage of a wide range of alloy, including zirconium-based alloys, and which with and without beryllium, are also alloys that contains phosphorus. And for the above mentioned characteristics, BMG are widely used in applications is here in space, nuclear, reactor engineering, biomedical, along with the electronic industry. Right? So, however, these characteristics also make the BMG hard to be machined by the conventional machining processes. So, unlike common glasses, which are electrical insulator, and BMG are good electrical conductivity, has good conductivity. So that's the reason we can use EDM to do it. So this is made possible to machine the BMGs using using EDM process, which removes the material by generating sparks between the electrically conductive tool and workpiece. So this is this one. So this is the result you should know. Okay. However, the major challenge of EDM BMG is to minimize the crystallization of the amorphous structure of BMG. The electrothermal energy used during EDM process may transfer the amorphous BMG to crystalline structure, thus deteriorating the unique property of BMG. So we want to investigate under what condition we want to minimize. We can minimize the recrystallization. So recrystallization is bad because we want amorphous material. So this you can take a look at this is the this introduction, right? So then I'm going to talk about this is the experimental setup, material and method, and I'm going to show you very beautiful pictures. So here is the micro EDM machine used in this study. We have here from here. This is the EDM power supply. We have a computer to record the results. And so we have EDM controller, motion controller in two directions, X and Y. And this algorithm control and digital I/O, and this is feedback. This is the axis, this is electrode. The electrode is rotating, is spinning, and also can go up and down. So here is the workpiece we want to machine. And so here's the table and the tank. So this is a spindle motor and to spin, and this is the electrode. So this tank is used to contain the electrical fluids for flushing the debris away. Right. So this is the setup. The material for our case we use this is zirconium-67. So use this kind of rich alloy, one alloy. So this is BMG now currently in the market, and there are several different kinds of BMG. But this BMG is what we use in our research. So here is the method. So this is the method for methodology followed during micro EDM of BMG. So you can just test it and set up workpiece tool, electrical machine parameters. In situ is micro electrode fabrication. This is electrode is micron, so you need to build your own micro electrode fabrication. So this one is built using this block micron EDG. So this is what we talk about in our when we talk about the fundamentals of EDM for fabricate high aspect ratio tungsten electrode. So here's a one machine measurement of fabricated electrodes and the reduction of diameter in the further steps. So here is you need to have this is micro electrodes first. Then application of fabricated micro electrode in blind hole machining using micro EDM. By the way, we use EDM to machine the blind hole, not through holes here in this research. Measurement and analysis on machine the optical and SEM. This is the characterization. So then we have EM modeling and simulation of phase transformation and crater. So this is methodology we use in our research. And for this is the text, and you can take a look if you have time. Right? So this is the material parameters we used in our research. Workpiece is a workpiece, electrode and sacrificial electrode. So this is micron electrode. The electric oil, we use EDM3 oil. Voltage, we apply. Capacitance and discharge energy. So this is a microjoule per pulse. Electrode rotation speed of the electrode is also given here. So here, this section talks about the in situ fabrication of tungsten microelectrode. I want you guys to take a look. So you can finally look at this one. Right, so this is in electrode. I might ask you guys and use your own language to tell me and how to build the tungsten microelectrodes. And the answer is here. I want you to read it and summarize and tell me something. That is on. Okay. This is how we get this microelectrodes. This is very, very beautiful. Do you agree? So experimental results and discussion. You can see this is experimental results. You can see. So these are for 3 different machining conditions. This one is the surface is not good, but this one is very, very uneven. Also here is also very good, but there's still some debris here. It's not debris. It's the bar here, bar along the edge. Remember the bar, right? Bar means the chip that is not separated from the piece. So here is SEM analysis. Crater size is a crater. How big the crater is? The different magnification. So here is a crater. The crater size. This is in fact of electrode diameter on the crater size. So different in the figure, a crater size is for 4 different constant electrode settings were compared for 2 electrode sizes. You can see the difference between different electrode diameters. So this picture shows the impact of voltage on the surface topography and finish of the blended microholes. This is very good, but there's still some bars, but it's very, very good. So here's the SEM analysis. This is a crater size and this overall card. This is a crater size versus capacitance. Capacitance is a parameter that you can control. Besides voltage, you can control. Discharge energy. So this is relationship between crater size and discharge energy is also given here. It's going on. Crater size versus capacitance. Crater size versus discharge energy. And then we talk about this is the modeling. This is the modeling here. The same thing, okay, very, very similar as the one we used for our. This is the EDM of the titanium 664. So here is a model. You can see this is a model. We have this heat flux because X is symmetric, and we just use this is 2D to mimic the 3D. So this is axial boundary. So these two boundaries, 2 edges, we use insulated boundary. So here is a convention boundary. Why is the convention boundary here? Because this is a fluid here, the electrical fluid. And so we have convention boundary here. So this is a model. And because we are going to focus on this area, so that's this area we use much finer mesh than other regions. So the total length is 50 micrometer, and this depth, the height is 100 micrometers. So here is a mechanical property and physical properties of BMT. This is a so this equation. We see this equation when we talk about numerical modeling of EM machining of titanium-64. We know these equations, and here this is the BMT mechanical and physical property of BMT. We have two different sites. One is a traditional, and one is a skilled unit. And why we need to have the skilled unit? Because we are handling the micro scale. But the Abaqus itself does not have units, and you need to specify these units and by yourself. So this is the units, this is the traditional units, and then we use this is a skilled unit, and skilled unit is for the micro scale model. The thermal conductivity is dependent upon the temperature, and this is given almost the linear one. So this one is the heat transfer. Dependency of the heat transfer on the temperature is also given. And so here is the phase transformation flow chart. Original is 300 K. This is the room temperature, and the glass transition occurs at 625 Kelvin, and crystallization occurs at 739 K, and melting, and the BMT melts. This BMT melts at 917 Kelvin degree. And simulation procedures is very similar to that one we have. So this is very similar, but I rewrite this equation because you cannot use your anything from the previously published papers. So here is this picture and shows the crater. This is the crater, radius of the crater. And so here is the original phase, and here is the molten phase, molten material, and this is the crystalline phase, and here is a super cool and liquid phase. We can have these multiple phases using different colors to represent. So here is the simulation results validation. As I always say, if you want to validate your models, you must compare your simulation results with the experimental results. You can see it's very close for different energy levels.